So, hello everyone, and of course, welcome back. I'm so excited to see all of you here. And today is our week number 5 from 6 weeks event journey of our Certified Community Edition Study Group. And my name is Anna Muzykina. I am Google Developer Group Ahlen organizer, Woman Tech Makers Ambassador, Woman in Data Science Ambassador, NASA Space Local Lead, and so on. AI enthusiast, AI innovator, AI engineer. Thanks to Arcada activity, I finished more than 400 labs, and of course most of them about AI. And today we have a big job to do, and we'll be exploring it in two distinct parts. So let's take a look at our agenda. We are diving into part 1 with an overview of the certification journey, emphasizing how this session sets the stage for success. The agenda includes intro to MLOps levels, pipelines, orchestration, and CI/CD to build your core knowledge. And we will work through sample diagnostic questions to identify gaps and, of course, prepare you for the certification exams. And in our part 2, we will explore TensorFlow extended components, prediction, environment, development, deployment, hardware, and this session will cover how these elements come together in practical applications. Of course, we will discuss their implementation and key considerations. So, this week, as the required homework will be to finish this course. So, first idea, of course, I'd like to watch together this 4 minutes introduction into this course with amazing explanation of what is MLOps. As I mentioned, from our Discord channel, not a lot of attendees start these courses. So please, let's explore and then understand that this is required courses which we are always asking you to finish. It's not something so big or hard to study.
Hi, my name is Esra Duygun, and I am a Google certified professional machine learning engineer and lead course developer. Welcome to Machine Learning Operations, or MLOps Fundamentals, the first course of the new series of machine learning operations topic. In the first series of courses, called Machine Learning on Google Cloud, you learn about how machine learning on Google Cloud can make tasks better, faster, and easier. The second series of courses, Advanced Machine Learning on Google Cloud, focuses on more wide-ranging machine learning applications, including computer vision, natural language processing, and recommendation systems. This series of courses is all about machine learning operations and focuses on machine learning models from an operational perspective. This particular course focuses on the MLOps concept and the considerations behind it. So, what is MLOps? MLOps is an ML engineering culture and practice that aims at unifying ML system development, or dev, and ML system operations, or ops, and guide teams through the challenges to the reproducibility of machine learning models. MLOps takes both its name and some of the core principles and tools of DevOps, because the goals of MLOps and DevOps are the same: to shorten the development lifecycle of systems and ensure that high-quality software is continuously developed, delivered, and maintained in production. The unique challenges and needs that machine learning poses, managing the lifecycle of data, models, and code, have led MLOps to quickly evolve as a domain of its own. This content is designed for dedicated or aspiring machine learning data scientists, engineers, and analysts who are interested in learning about machine learning in the cloud and using ML models and Vertex AI. To get the most out of this specialization, it is recommended you have proficiency with Python on topics covered in the crash course on Python offered by Google, and prior experience with foundational machine learning concepts and building machine learning solutions on Google Cloud, as covered in the Machine Learning on Google Cloud courses. In the first part of this course, Employing Machine Learning Operations, you explore machine learning models from an operational perspective. First, you examine the challenges that machine learning practitioners face when they operationalize ML models and make them available for production. From there, you get an introduction to the concept of DevOps in machine learning. And finally, you explore the machine learning. In the second part, what is Vertex AI and why does a unified platform matter? You learn about Vertex AI and its importance. Then you discover the MLOps capabilities of Vertex AI. Finally, you explore how Vertex AI helps with the MLOps workflow. Through a hands-on lab at the end, you work on a high-value real-world use case, predicted customer life value, or CLV in short. You'll start with a local BigQuery and TensorFlow workflow that you might already be familiar with, and progress toward training and deploying your model in the cloud with Vertex AI. You also test your knowledge throughout the course with graded assessments. After you complete this course, you will be able to see ML projects from an operational perspective. You will understand the concept of DevOps in ML and why you need to operationalize your ML models in a unified app platform like Vertex AI. Enroll today to learn about machine learning operations.
So it was introduction into required course, which I'll share to you at the end of the session and of course at Discord channel. So as we heard from this introduction, let's summarize what MLOps is. So MLOps, or machine learning operations, is the practice of taking a trained machine learning model and deploying it into a production environment. So it's about the collaboration between data scientists and operations team to make sure that models are built and managed in reliable, repeatable way. And MLOps is so important for a professional machine learning engineer because, of course, it ensures that your model are not only accurate but also scalable and can be easily updated and of course can be monitored for performance in the real world, which is crucial. So many people think that building an ML model is the main challenge, but as the slide shows, that's not the case anymore. The small red box in the middle, labeled ML code, is just a teeny fraction of a real-world machine learning system. The real work is in all these blue boxes around it. For a model to actually work in a real-world setting, it needs a complete system for data collection, feature engineering, serving predictions, and especially monitoring and automation. The real challenge today is not just building the model, but also building the entire, all this complex system to support it. So, to dive deeper into this topic, what exactly is MLOps and how it is related to data science? As you can see from the diagram, and of course from previous video, MLOps sits right at the corner of three very important disciplines: data engineering, data science, and software engineering. From data engineering, MLOps takes the best practices for building robust data pipelines. From data science, it takes the skills for building and prototyping models. But from software engineering, it adopts the principles of building scalable systems and using processes like CI/CD, continuous integration, continuous deployment. Of course, we will dive deeper into CI/CD in our next slides. So, by combining all these three, MLOps allows us to take a model from a data science notebook and deploy it as a releasable, scalable product. But of course, it's important to summarize the MLOps process. So we can break it down into three main stages. First, as you can see on the left, we have a machine learning stage. This is where the core data science work happens. It including tasks like data processing, model development, and metric evaluation. In the middle, you can see development stage. This is where we integrate the model into large system by building CI/CD pipelines and calculating things like latency. And of course, finally, on the right, we have the operations stage. This is where the models is running live in the real world. Here, exactly here, we focus on continuous monitoring. It's crucial. Getting user feedback loop and making sure that the model delivery is working smoothly. Okay, now that we have a better understanding of what MLOps is, let's move on our next topic, pipelines. So, what is the best way to maintain pipelines on Google Cloud? And don't worry, we will dive deeper into this meaning of pipelines, what it is later. So, the best way, Vertex AI pipelines, and this is a solution for building and managing your machine learning pipelines. It's a managed version of Kubeflow, which means you don't have to worry about the underlying infrastructure. And the main purpose of using Vertex AI pipelines is that it helps practitioners in two key ways. It accelerates productionization and ensures the standardization of your AI workflow. So, let's dive deeper. What exactly is a pipeline? A pipeline is a series of modular components or pieces that are chained together to form a workflow. As you can see from this image, these components offer automation and orchestration for our machine learning process. A Kubeflow pipeline is defined using a Python function. The different steps in the workflow are created using Google Cloud Pipeline components. And you define the flow of the pipeline as graph. Once you have defined your pipeline, you compile it using a compiler. And finally, you create and run the pipeline on Vertex AI pipelines, of course, using the Vertex AI client. Okay, but how do we actually go about building a pipeline? First, before Vertex AI pipelines can work its magic, you must describe your workflow as a pipeline. This means you lay out the steps your model needs to take. The great thing is that these pipelines are portable and scalable because they are based on containers and Google Cloud services. The next question is, which SDK should we use? So, if a workflow uses TensorFlow to process huge amount of data, Feel free to build your pipelines using TensorFlow Extended or TFX. We will dive deeper later. And for other UKs, you should use the Kubeflow Pipelines SDK. This lets you create custom components or reuse pre-built ones from Google Cloud. Okay, and what if we define our pipeline workflow using a package called Kubeflow Pipelines Domain Specific Language Package, or KFP DSL? This package contains the DSL that you use to define and interact with pipelines. The core building blocks of a pipeline are the Kubeflow pipeline components, and each component is a self-contained step that describes its inputs, outputs, and what it does. The components are then used to create the steps in your pipeline. A key thing to remember is that a step only runs when the data it depends on becomes available. So, for example, a training component will only run after a data preprocessing component has finished and produced its output. And let's now look at the first step of our workflow, which is to create a data set generator. This step uses a Google Cloud pipeline component, and we provide it with the necessary information or input arguments. And it uses a Python variable called DSOP to define the output. I underlined by red. It's important to understand that this variable only holds the definition of the data set, not the actual data itself. The data set's values is not accessible at this point. It can only be used by providing it as an input to the next step in the pipeline, which we called a downstream component. The second step of our pipeline is a model training component. It takes the data set that we created in the first step and uses it as an input. And you can see this is the code where the data set variable is used. And I underlined by red this variable data set. The output from this step, which includes the trained model, will then be stored in a variable called training job run OP, as shown here and underlined with red. And the third and fourth steps of our pipeline are for deploying the model. First, we create an endpoint. You can think of endpoint as a secure entry point that allows other applications to access your model and get predictions from it. Then, as the next step, we deploy our trained model to this endpoint. And when we do this, we set a minimum replica count and maximum replica count. The minimum replica count is the smallest number of nodes or virtual machines that will be running your model at all times. This ensures your model is always available. And the maximum replica count is the largest number of nodes your model can scale up to. If there is a huge demand for predictions, the system will automatically add more nodes up to this maximum number to handle the load. And once the steps of your pipelines are defined, the next things you need to do is compile it into a JSON file. This file will contain all the necessary information for the pipeline to run on the Vertex AI service. After the pipeline is compiled, you can use the Vertex AI Python client to submit and run your pipeline. The code on the bottom of the slide shows you how you can create a job and submit it to the Vertex AI service. So, let's take a look at our simple first questions. For example, you are developing an ML pipeline using Vertex AI pipelines. You want your pipeline to upload a new version of the XGBoost model to Vertex AI model registry and deploy it to Vertex AI endpoint for online inference. You want to use the simplest approach. What should you do? So, from this list of answers, of course, correct answer is D. Change the Vertex AI model upload OP and model deploy OP components together. D uses the pre-built Vertex AI model upload OP and model deploy OP components, which are designed exactly for this purpose. Chaining them together is the most straightforward and simplest way to accomplish the task. Options A and C involve writing custom components or using APIs directly, which is not the simplest approach. So option B is for evaluating a model, not for deploying it. Next example of this sample question is: imagine you are building a custom image classification model and plan to use Vertex AI pipelines to implement the end-to-end training. Your dataset consists of images that need to be pre-processed before they can be used to train the model. The pre-processing steps include resizing the images, converting them to grayscale, and extracting features. You have already implemented some Python functions for pre-processing tasks. Which components should you use in your pipeline? Based on the problem's requirements, the correct answer is, of course, B, because it's only option that addresses both key needs of the pipeline: custom preprocessing and custom training. If we take a look at options A, data proc spark batch OP and custom training job OP, and options B, data flow Python job OP, wait GSP resource OP, and custom training job OP. So if we analyze this, we can see that the preprocessing tasks which use Python function are a perfect fit for a data flow job. So we should use the data flow Python job OP component. And since we are building a custom model, we need to use a component for custom training, which is, of course, the custom training job OP. The wait GSP resource OP is a general purpose component for waiting for resources, which is a common task in a pipeline. And option A uses data proc, which is not ideal for Python functions. So option D uses AutoML, which is, of course, not for custom models. That's why the correct answer is B. And if you look at another sample question, imagine You are creating a model training pipeline to predict sentimental scores from text-based product review. You want to have control over how the model parameters are tuned, and you will deploy the model to an endpoint after it has been trained. You will use Vertex AI pipelines to run the pipeline. You need to decide which cloud pipeline components to use. What components should you choose? So, based on the problem-specific requirements, the answer is D, because it's only option that addresses all three key components of the pipelines. Let's take a look. For example, a text data set create OP. The problem specifies that you are working with text-based product review. So this component is the correct choice for creating a data set from this type of data, which eliminates options A and C. And custom training job OP. The problem states that you want control over how the model parameters are tuned. Of course, this component is used for training models with custom code, giving you that control. This is a key reason why option B, which uses an automated training component, is incorrect. And model deploy OP, the problem's final requirements is to deploy the model to an endpoint. This component is specifically designed to handle this task. So that's why option D is the only choice that correctly combines the components needed for creating a text data set, training a custom model, and deploying it. Okay, so before we move to our next sample question, let's stop for a moment and at orchestration. What is orchestration? In machine learning, it's the process of automatically managing and coordinating the different steps of an ML pipeline. Think of it like a conductor in an orchestra. The conductor doesn't play the instruments, but he or she makes sure everyone plays in the right order at the right time. This is a key part of MLOps because it allows you to build automated, repeatable, and reliable ML systems that can run in production without manual intervention. It makes your workflow more efficient and less prone to errors. And of course, if you will follow our recommendation and finish courses we will asking you to finish during next week, you will dive deeper into orchestration. So let's look at the sample question exactly related to this topic. Imagine you are creating an ML pipeline for data processing, model training, and model deployment that uses different Google Cloud services. You have developed code for each individual task, and you expect a higher frequency of new files. You now need to create an orchestration layer on top of these tasks. You only want this orchestration pipeline to run if new files are present in your data set in a cloud storage bucket. You also want to minimize the compute node costs. So, what should you do? Let's analyze the requirements. The key is to run the pipeline only when your file arrives and to minimize costs. Because as the question was to run if new files are present. This means we need an event-driven solution and not a periodic one. So let's summarize. Option A is exactly a periodic solution, which would run even if there are no new files. So it's not cost effective. Option B, C, and D are all event driven. They are all valid approach, but some are more direct than others. Option D uses a cloud composer, which is sensor, and which is a great solution for this, but it may not be the most straightforward. Option C uses a cloud function that is triggered by a new file. The cloud function then deploys the Vertex AI pipeline, and this is a very common and effective pattern for event-driven pipelines on Google Cloud. And it's a direct way to connect an event in cloud storage to a pipeline run in Vertex AI. Therefore, the correct answer is C. Create a pipeline in Vertex AI pipelines. Create a cloud function that uses a cloud storage trigger and deploy the pipeline. Okay, let's move on to our next section, CI/CD. CI/CD, which stands for continuous integration and continuous deployment, is a core practice in MLOps. The goal is to automate the process of building, testing, deploying your machine learning models to production. This makes the entire workflow more efficient and reliable. So, as you can see, ML development process, a journey that starts with data engineering on the left and moves throughout experimentation and prototyping in the middle and ends with training formalization on the right. This entire process is what we need to have in place before we can even begin to think about the ICD. We need a repeatable, formal process for training our model before we can automate it. So, let's now look at how CI/CD fits in this picture and helps us automate this entire workflow. The next step in our workflow is training operationalization. This is all about automating the process of creating, testing, and deploying a reliable training pipeline. We do this by using ML pipelines, which contain all the configurations needed and to deploy our workflow. And these pipelines are then managed by CI/CD processes. And first, in this CI stage, we test our code and build a training pipeline. Any artifacts like container images are stored in a repository. Then, in CD stage, we deploy the pipeline to a production environment. We perform a quick test called a smoke test to make sure it works. If it fails, the system can automatically fall back to the previous working version. This process produces two key assets: the training pipeline executable components, our containers, and a record of the pipeline run. It leverages core MLOps capabilities like ML pipelines, CI/CD, and version control. Let's dive deeper into what the automated workflow looks like. The diagram at this slide shows a visual representation of a training pipeline delivery workflow. The process is triggered when new code is pushed to your version control system. First, we enter the continuous integration stage. Here, the code is built and tested. If the tests pass, we move to continuous delivery. The pipeline is first deployed to a staging environment for more throughout testing. If it passes those tests, it is then deployed to the production environment. Finally, in the production deployment stage, the new training pipelines is released. We can even run smoke tests here to ensure that everything is working correctly before the final release. This entire process is what allows us to reliably and automatically update our training pipelines. And now that we have seen the conceptual workflow for CI/CD, let's look at a key tool on a Google Cloud that helps us make it happen: Cloud Build. As you can see from the diagram, the process starts with our source code. When there's a change to the code, it activates a trigger. This trigger starts Cloud Build, which then runs a series of build steps. These steps are where our code is built, tested, and where we create the container images we need for our pipelines. Cloud Build is a managed service that runs these steps in parallel, making the entire build process fast and reliable. Okay, now that our code has been built and tested by Cloud Build, the next logical step in the process is continuous training. Continuous training is all about repeatedly executing the training pipeline in response to changes in data, changes in code, or on a schedule. This is crucial for making sure our model stays relevant over time. A typical workflow for continuous training involves a few key steps. It starts with data ingestion, then moves to model training, evaluation, and finally registration of the model. All the information from each run is automatically tracked in a metadata and artifacts repository. This is incredibly helpful for debugging, reproducibility, and understanding the history of our model. This process produces two key assets: a trained and validated model that is stored in a model registry, and a set of training metadata and artifacts that are stored in a repository. This entire process is powerful by core MLOps capabilities like data processing, model training, and of course model evaluation. So the continuous training pipeline starts with a retraining trigger, which can be activated by changes in the data set, data validation, or even other factors. The workflow then proceeds throughout dataset ingestion and data validation to ensure that the quality of the incoming data. If data issues are found, they are routed back to the dataset and feature repository for correction. Next, data transformation prepares the data for model training, leveraging a data processing engine. This is followed by model training tuning, which uses a model training engine. The trained model then undergoes model evaluation and model validation using a model evaluation engine. If the model passes validation, it proceeds to model registration. Throughout this entire process, all run information, metadata, and artifacts are stored and, of course, tracked into an ML metadata and artifact repository. This is crucial for debugging, reproducibility, and understanding the lineage of the model and data. This slide also shows that outputs like the data set, trained model, and training pipeline, metadata, and artifacts are produced and stored appropriately. Model deployment, which is a crucial stage in the MLOps lifecycle. It involves packaging throughout testing and then deploying a trained machine learning model to a serving environment, enabling both online experimentation and production serving. The process heavily relies on CI/CD principles. Here's how it generally works. So, source code and model integration is where the CI/CD system reads the source code of the component responsible for serving the model from a source repository. It then fetches the trained model from the model registry. Building and validation. The system integrates, builds, tests, and validates the model serving services. This includes testing the model's interface to ensure it accepts the expected input format and produces the core output. Compatibility with the target infrastructure is also validated during the CI stage. In the CD stage, the development is often managed throughout a progressive delivery progress. This means the model isn't immediately rolled out to all users. Instead, methods like smoke testing are used to quickly check the efficiency of the model's service. For example, latency throughput, and identify any service errors. The model's effectiveness in a production environment is also tested. Commonly, throughout online experiments such as A/B testing or multi-armed bandit testing. This helps compare the new model's performance against existing versions. So, this slide highlights the core MLOps capabilities that support model development, model deployment, model serving, model registry, online experimentation, ML metadata and artifact repository. And so finally, the typical assets produced from this stage are a model serving executable application and online experimentation evaluation metrics, which are crucial for assessing the success of new model deployment and are stored in the ML metadata and artifact repository. Okay, let's explore model deployment. The model deployment, as you can see, this diagram showing how a trained model moves from being a candidate model to a production model. The flow starts with a registered model, which signifies a model that has successfully completed the training and validation phases and is stored in the model registry. This registered model then enters a CI/CD process represented by the build and test stages. These steps involve preparing the model for serving, such as packaging it into a deployable artifact and conducting initial tests to ensure its functionality and Compatibility. After successful testing, the candidate model is then deployed to the production environment. This deployment process is also followed by further test steps, likely more comprehensive integration and smoke tests in the live environment. Throughout this entire workflow, all relevant information, including the registered model details, the candidate model status, and the production model versions, along with all artifacts and metadata, are tracked and stored into the ML metadata and artifact repository. This repository is critical for maintaining lineage, enabling reproducibility and facilitating debugging if issues arise in production. And here you can see a detailed visual representation of how a model serving component moves from development to production throughout a continuous delivery process. The workflow is triggered by a deployment trigger and begins with continuous integration. Source component and registered model are used, as you can see. The package step involves creating a deployable serving package. Integration testing is performed to ensure the components work together. All relevant binary component and source component information is stored in the software artifact repository. And next is the continuous delivery stage. The serving package is deployed to staging, used a model serving engine staging. Acceptance testing is conducted in the pre-production environment. If successful, the model is then deployed to production using model serving engine production. The production development involves advanced strategies to minimize risk. As a canary deployment, gradually rolling out the new version to a smart subset of users. At the part where you can see shadow deployment, you see this violet part at the middle. So here running the new model alongside the old one, but only routing a copy of live traffic to the new model for evaluating without affecting users. Blue-green deployment is the next after shadow deployment. It's where having two identical production environments where the new version is deployed to an inactive environment, fully tested, and then traffic is switched over. Online experimentation techniques like A/B testing and MAB testing are used to compare the new model's performance with existing ones. And here at online experimentation, you see smoke testing is performed to quickly verify basic functionality. Throughout the entire process, version control tracks all code changes. The model registry stores and manages different versions of the trained models. The ML metadata and artifact repository is used to store and track all evaluation metrics, serving package, and other crucial metadata enabling debugging, reproducibility, and lineage. A rollback mechanism is in place, allowing a quick return to a previous stable version if issues are detected at any stage. So, predicting serving is the process of making your deployed models available for inference. It needs to handle various types of predictions, such as real-time online and streaming prediction, as well as offline batch and embedded predictions. The outputs of these predictions often include not just the result, but also feature lookups and explanations for models' rationale. The key MLOps capabilities that power these are a dataset, feature repository, and the core model serving infrastructure itself. The outputs we get from this process are typically request, response, playlouts, and feature attributions. Let's take a look at detailed overview on the prediction serving process, which is the final stage where your deployed model is used to make predictions. And after, we will move to our next simple questions. So, the process starts on the far left where a model deployment creates a package model. This package is then sent to the model serving system, which is the heart of the operation. The model serving system can handle various types of prediction, including online, batch, streaming, and embedded inference. It also has the ability to fetch additional data from a serving feature lookup to make better predictions. The result of these predictions, along with explanations, are then sent to a model consumer. All of the activity is logged and stored in an ML metadata and artifact repository, which is then used by a model monitoring engine to ensure the model's ongoing health and accuracy. So, let's move to our sample questions. Imagine you developed a Vertex AI ML pipeline that consists of pre-processing and training steps, and each set of steps runs on a separate custom Docker image. Your organization uses GitHub and GitHub Action as CI/CD to run unit and integration tests. You need to automate the model retraining workflow so that it can be initiated both manually and when a new version of the code is merged into the main branch. You want to minimize the steps required to build the workflow while also allowing for maximum flexibility. How should you configure the CI/CD workflow? So, the question asks how to configure the CI/CD workflow. The correct answer A is trigger a cloud build workflow to run tests, build custom Docker images, push the images to artifact registry, and launch the pipeline in Vertex AI pipelines. So this approach is optimal because cloud build integration, cloud build is Google Cloud's native CI/CD service, specifically designed for building Docker images, pushing them to artifact registry, and orchestrating deployment with Google Cloud, including Vertex AI pipelines. This provides a streamlined and efficient integration. Uh, from side automation, it automates the entire process from code change to pipeline launch. And about flexibility, while GitHub Actions can initiate the overall process, delegating the heavy lifting, image building, pushing, pipeline launching to cloud build leverages Google Cloud Specialized Service, offering a robust and flexible solution. So, other options B, C that involve GitHub Actions directly building Docker images or launching Cloud Run for image building might introduce more complexity or less native integration within the Google Cloud ecosystem for this specific task. Option D, while mentioning triggering cloud build via GitHub Actions, is structured in a way that makes option a more direct and often preferred integration patterns for this type of workflow. So let's move to next question. Imagine your team frequently created new ML models and runs experiments. Your team pushes code to a single repository hosted on a cloud source repositories. You want to create a continuous integration pipeline that automatically retrains the models whenever there is any modification of the code. What should be your first step to set up the CI pipelines? The correct answer is, of course, B. Configure a cloud build trigger with the event set as push to a branch. Here, let's discuss why. So, let's discuss automatic retraining on code modification. The core requirement is to trigger retraining whenever there is any modification of the code. A push to branch trigger in cloud build is specifically designed for this purpose. When code is pushed to the repository, for example, the main branch, this event will automatically activate the cloud build pipeline, which can then handle the retraining process. Cloud build's role is Google Cloud integrated CI/CD service, making it the natural choice for setting up triggers and orchestrating build and deployment workflow within Google Cloud, and minimizing steps using a native cloud build trigger directly connects code changes to the CI pipeline, minimizing manual configuration or external services. So, other options are less suitable. A pull request trigger, while useful for code review, it doesn't directly trigger on any modification to a branch, as the question implies an automatic retraining upon merge. C and D, so cloud function for building the repository. While cloud function can be triggered by repository events, cloud build offers a more comprehensive and purpose-built CI/CD solution for building, testing, and deploying code, especially for ML pipelines with Docker images. Using cloud functions for the build itself would likely be more complex than necessary compared to a direct cloud build trigger. So that's why answer B is a correct one. Configure cloud build trigger with the event set as push to a branch. This will be enough. Okay, and let's take a look at another simple question. Let's imagine you recently deployed a pipeline in Vertex AI pipeline that trains and pushes a model to a Vertex AI endpoint to serve real-time traffic. You need to continue experimenting and iterating on your pipeline to improve model performance. You plan to use Cloud Build for CI/CD. You want to quickly and easily deploy new pipelines into production. And you want to minimize the chance that the new pipeline implementations will break in production. What should you do? So, of course, option C is the most appropriate. Here you can see pre-production environment, successful pipeline run validation, CI/CD automation. Let's take a look. So, pre-production environment. Deploying to a pre-production environment staging first is the best practice in CI/CD. It allows for comprehensive testing of the new pipeline implementation in an isolated environment, mimicking production conditions but without affecting live traffic. Waiting for a successful pipeline run in the pre-production environment before deploying to production directly addressing the need to minimize the chance that the new pipeline implementations will break in production. This ensures that the entire end-to-end process, data ingestion, training, model evaluation, and registration, works as expected before going live. And CI/CD automation. The option correctly emphasizes settings up a CI/CD pipeline using Cloud Build as specified in the problem to automate the build test and deployment steps. Other options are less suitable. As you can see, the A, manual upload. This option suggests using the Google Cloud Console to upload build containers and compiled pipelines. This is manual process and goes against the goal of automating deployment and the principles of CI/CD. B, unit tests in pre-production. While testing in pre-production is good, until tests are typically run earlier in the CI stage on the source code. A pre-production environment is for more comprehensive integration and end-to-end testing, including the full pipeline run. And as D, rebuilding source code before production. So rebuilding the source code again just before deploying to production is unnecessary and can introduce inconsistencies. The artifact should be built once and then promoted throughout environments after the successful testing. So that's why only C is the most appropriate answer. Okay, so my congratulations, we finished part 1 and let's move to the part 2 and start with TFX components. I think you are a little bit tired, so now let's take a 7 minutes rest by watching this 7 minutes video.
So you've built your machine learning models, and now it's time to take them to production. What do you need to do? Stay tuned to find out. Welcome to AI Adventures, where we explore the art, science, and tools of machine learning. I am Priyanka Vargaria, and today we are going to talk about managing production machine learning pipelines. As you've seen through years of AI adventures, machine learning is a lot of fun and is much more than just a novelty. Machine learning models power so many technologies in our lives, and there are plenty of new and better models just waiting to be applied to the real world. So, how do you transition from experimenting with a model to actually moving it to production? Well, just as you need a quality CI/CD pipeline to maintain a robust code base at scale, you need a machine learning pipeline to help you monitor, transform, evaluate, and serve your models in production. What are the different steps involved in a machine learning workflow? Well, first, you ingest the input data set and split it for training, evaluation, and testing. Then, validate it, identify and remove anomalies from that data, or handle redundant features and empty values. You might have to address the detected issues, maybe finding more training data for certain categories. Then you do feature engineering to transform the data and enrich the features to improve your training. At which point, the model is ready to train and tune. Once trained, evaluate the model to make sure it generalizes well enough to use in production. When the model gets the green light, you push it to production. This production environment needs to be powerful enough to support the rate of inference required by your application. Now, when does this ML workflow becomes a pipeline? Well, it's when we automate it. And the automation is necessary, especially if we want to deploy these models in production. So the question now becomes, how do we automate the machine learning workflow tasks to create an end-to-end pipeline for deploying our models into production? Here is a very high-level architecture of how it works. TensorFlow is running on TFX, which in turn is running inside Kubeflow pipelines, and that's running on GKE, leveraging the Google Cloud services. You can create pipelines with similar functionality using both Kubeflow pipelines and TensorFlow Extended SDKs. We have an entire series on Kubeflow, which I have linked below. In this video, let's focus on TensorFlow Extended, or TFX, which is an open source end-to-end platform specifically designed for scalable, high-performance machine learning tasks. Here's how it works. A TFX pipeline is a sequence of components implementing the ML workflow tasks, and they are built using open source TFX libraries, which can also be used individually. This is sort of a canonical TFX pipeline. You can think of it as Hello World pipeline. These orange components come out of the box with TensorFlow Extended, but you can create your own components as well. Once the model is ready, you deploy it into a serving cluster in TensorFlow Serving, TensorFlow JS, TensorFlow Lite, TensorFlow Hub, or even AI platform predictions. Now, what is a TFX component? It is essentially a task that we perform in our machine learning pipeline. It has a config and it takes input from the metadata, except for the very first component, which is ingesting the data set from the original data source. It takes those inputs using an input channel, does its task, and generates the output artifact, and then uses the output channel to put those back into the metadata. And that's how components communicate with each other. The upstream components will produce an artifact that the downstream component depends on, and the data flows through the pipeline by flowing through these dependencies in the metadata. Now, what is metadata? Well, it allows us to trace the lineage of the artifacts that are produced. For example, what data is the model trained with? Metadata can also be used to compare previous training runs. It also allows tracking and reuse of previously computed outputs, which saves quite a bit of time, especially for larger data sets and models. If the input to the component has not changed, we don't want to rerun the component. We should just be able to pull the last result from the cache and reuse it. Now let's go back to our standard components and understand them a little bit more. First off, example gen. helps us ingest our data from CSV files, BigQuery, Presto, etc. It splits the data and saves it off as TF examples and TF record files. Statistics Gen will make a full pass over that data and calculate statistics about it. That's important to understand our data if it is new and if it has changed over time. Schema Gen then determines the schema across our data, such as what are the types of our features, and for the categorical variables, what are the valid categories. Example Validator takes both of those results and looks for problems, things like the examples that have the wrong type in the particular feature or a categorical value that should not be there. Transform is where the feature engineering is done. It will convert the feature engineering that we want to do with a graph that becomes part of our model. Trainer takes that graph and the model that we have defined using TensorFlow and trains that model. Evaluator takes that trained model and does a deep analysis of the performance of that model. It looks at not just the entire data set, but also the individual slices of a data to try to understand how performance varies across different parts of our data. It can be used for fairness analysis, like seeing if your model is performing differently for different types of model users. Infra Validator makes sure that we can actually deploy our model to our serving infrastructure. If both Evaluator and Infra Validator agree that yes, we can deploy our model, our evaluator has checked to make sure that the model is actually better than what we have in production, then the pusher will push it to one of our deployment targets. So that was a quick overview of TensorFlow Extended, which helps engineer our machine learning pipelines so we can deploy our models in production.
Okay, I hope you rest a little and have move to the part number 2, and we need to explore TensorFlow Extended. So let's dive deeper. Now we can summarize after watch video. So TFX or TensorFlow Extended is an end-to-end platform for building and deploying production machine learning pipelines. It provides a set of standard reusable components that can be easily connected to form a complete ML workflow. Each TFX component performs a specific task within the pipeline, such as data ingestion, pre-processing, model training, or deployment. Using these standard components helps to standardize and automate your ML process, making it more efficient and reliable. You can also create custom components to extend your ML workflow to meet your specific needs. TFX is built on top of TensorFlow and is designed for scalable, high-performance machine learning tasks. TFX offers 3 main capabilities. A toolkit for building ML pipelines. It enables orchestration of ML workflows on platforms like Apache Airflow, Apache Beam, and Kubeflow pipelines. A set of standard components. These pre-built components can be used within pipelines or directly in ML training scripts, providing proven functionality. And libraries. TFX includes underlying libraries that support its standard components, allowing users to create custom components or use the libraries independently. So, okay, now let's talk about the prediction environment. The prediction environment is our next step. So, what does it mean? The prediction environment is the infrastructure where your trained model is deployed to serve predictions. This is a crucial part of MLOps lifecycle. as it's where your model goes live and starts to provide real value. It involves everything from selecting the right hardware to setting up a secure and scalable serving service. But how you request predictions from your deployed model? Vertex AI provides three main ways to do this. First, you can use batch prediction. This is used when you need to make predictions on a large number of examples at once and you don't need the results in real time. Second, you can get online predictions from AutoML models. This is for when you need real-time predictions from a model that was trained using the automated services on Vertex AI. Finally, for more custom needs, you can use pre-built containers and custom containers. This gives you the flexibility to deploy a wide range of models, not just those from AutoML, and even provide your own code for prediction and explanation. When you're satisfied with your model's performance during the validation cycle, it's time to deploy your model. Perhaps that means production scale usage, or maybe it's a one-time prediction request. Depending on your use case, you can use your model in different ways. Batch prediction lets you make many prediction requests at once. Batch prediction is asynchronous, which means that the model will wait until the process all of the prediction requests before running a CSV file for BigQuery table with prediction values. Or online prediction is useful if your model is part of an application and part of your system are dependent on a quick prediction turnaround. Deploy your model to make it available for prediction requests using a REST API. Online prediction is synchronous in real time, which means that it will quickly return a prediction but only accepts one prediction request per one API call. Vertex AI provides Docker container images that you run as pre-built containers for saving predictions and explanations from trained model artifacts. These containers, which are organized by machine learning framework and framework vision, provides HTTP prediction servers that you can use to serve predictions with minimal configuration. In many cases, using a pre-built container is simpler than using a custom container. To use a custom container to serve prediction from a custom trained model, you must provide Vertex AI with a Docker container image that runs an HTTP server. Specifically, the container must listen and respond to liveness checks, health checks, and prediction requests. But what about the requirements for running predictions on Vertex AI? It's important to understand these requirements to ensure your job runs smoothly. On the left, we have the requirements for a BigQuery table data source. The table size must not be larger than 100 gigabytes and the dataset must be multi-regional. If the table is in a different project, you must have the BigQuery data editor role for the Vertex AI service account in that project. On the right, we have the requirement for a CSV file data source. The file must not be larger than 10 gigabytes, but you can include multiple files up to maximum of 100 gigabytes. The first line of the file must contain the name of the columns. If the cloud storage bucket is in a different project, you must have the storage object creator role for the Vertex AI service account in that project, and this is crucial. So, okay, let's move to our next sample questions. Imagine you recently trained a XGBoost model that you plan to deploy to production for online inference. Before sending a predict request to your model's binary, you need to perform a simple data preprocessing step. This step exposes a REST API that accepts requests in your internal VPC service, controls and returns predictions. You want to configure this preprocessing step while optimizing cost and effort. What should you do? It asks how to deploy an XGBoost model with preprocessing. Goals are minimizing cost and effort for online inference. The correct answer is, of course, D. Use a custom predictor based on a Vertex built-in container. Store the picked model in cloud storage. Deploy to Vertex AI endpoints for a REST API. Let's take a look at why D is the best choice and why the other options are less ideal. Option D, build a custom predictor class based on XGBoost predictor from the Vertex AI SDK and package the handler in a custom container image based on a Vertex built-in container image. Store a picked model in cloud storage and deploy the model to Vertex AI endpoints. So, using a Vertex AI built-in container image as a base significantly reduces the development effort and cost associated with creating a custom container from scratch. These built-in images are pre-optimized for various ML frameworks, including XGBoost. Building a custom predictor class allows you to integrate the required simple data preprocessing logic directly into the model serving pipeline. This addresses the need to perform preprocessing before sending prediction requests and exposes a REST API. Storing the picked model in cloud storage is a standard and cost-effective practice for managing model artifacts. The serving environment, Vertex AI endpoint, can easily load the model from this location. This approach is flexible, especially if you need to update the model frequently, as you don't need to rebuild the entire container image each time. Vertex AI endpoints are specifically designed for serving models for online inference with low latency and high availability. They support auto-scaling to handle fluctuating traffic and can be configured to work within internal VPC service controls. Meeting the security requirements, the Vertex AI SDK provides the tools to build and deploy predictors to these endpoints efficiently. So, in summary, option D provides a comprehensive solution that leverages Vertex AI's capability to minimize cost and efforts, integrate the preprocessing step, store the model efficiently, and deploy it for low latency online inference with the required security configurations. Okay, Let's move to the next question. Imagine you have developed an application that uses a chain of multiple scikit-learn models to predict the optimal price for your company's products. Members of your team use the individual models in other solution workflow. You want to deploy this workflow while ensuring version control for each individual model and then overall workflow. Your application needs to be able to scale down to zero. You want to minimize the compute resources, utilization, and the manual effort required to manage this solution. What should you do? The correct answer for this question is D, because it offers the most suitable approach for deploying a workflow of chain scikit-learn models for an online grocery store application meeting the requirements for version control, scalability down to zero, and minimizing compute resource utilization and manual management effort. So, if we break down why that is the best choice and why the other options are less ideal, let's take a look. Option D. Load each model's individual files into Cloud Run. Use Cloud Run to orchestrate the workflow. Track the version of each individual model in BigQuery. Okay. Scale to zero and minimize compute effort. It was our task. Cloud Run is a fully managed serverless platform that automatically scales based on incoming requests, including scaling down to zero when there is no traffic. This aligns perfectly with the requirements to minimize compute resource utilization and manual management effort, as you only pay for the resources used when the service is active. Cloud Run is well suited for orchestrated workflow by chaining different services. You can create a custom service on Cloud Run that acts as the main application logic, calling other Cloud Run services, each hosting an individual scikit-learn model in the required sequence to execute the change workflow. By loading each model's individual files into separate Cloud Run services or managing them within a monorepo structure handled by Cloud Run, you enable independent versioning and deployment of each scikit-learn model. This is crucial for maintaining version control for each model in the chain. And using BigQuery to track the versions of individual models provides a robust and scalable solution for managing metadata, lineage, and historical data. This fulfills the requirements to track version effectively. So, option A and C expose individual models as Vertex AI endpoints, while Vertex AI endpoints are excellent for serving individual model with low latency and auto-scaling. Creating an endpoint for each individual model in a chain of potentially many models can lead to higher overhead and more complex management compared to a streamlined Cloud Run approach. The scale down to zero requirements is also more effective met by Cloud Run. And option B, custom container endpoint, load individual files, track in BigQuery. So using a custom container endpoint might not provide the same level of serverless management and scale down to zero benefits as cloud run. Managing a custom container endpoint for multiple models could also be more complex. So, in summary, option D provides a comprehensive solution that leverage cloud run serverless capabilities for efficient scaling and orchestration, combined with BigQuery for robust version tracking to meet all the specified requirements for deploying the scikit-learn model workflow. And let's take a look at this simple question. When you recently trained an XGBoost model on tabular data, you plan to expose the model for internal use as an HTTP microservice. After deployment, you expect a small number of incoming requests. You want to productionize the model with the least amount of effort and latency. So, what should you do? The correct answer, of course, will be D, because it offers the most straightforward and efficient approach for deploying an XGBoost model as an HTTP microservice with minimal effort and low latency for a small number of requests. So let's take a look why exactly D our best choice. So option D, use a pre-built XGBoost Vertex container for deployment. Deploy the model to Vertex AI endpoints. Using a pre-built XGBoost Vertex container significantly reduces the effort required for packaging and setting up the serving environment. These containers are optimized for XGBoost models and handle many of the underlying complexities. Deploying the model to Vertex AI endpoints provides a managed service designed for low latency online interference. Vertex AI endpoints are built to handle real-time prediction requests efficiently. Vertex AI endpoints naturally expose the deployed model as an HTTP microservices, fulfilling these requirements of the question. And while Vertex AI endpoints can scale to handle high traffic, they are also suitable for scenarios with a small number of requests, providing a cost-effective solution without the need for complex manual scaling configurations. So, and why other options are less suitable? Let's take a look. The specific details of options A, B, and C are not provided in the user query or active context. So, a general comparison based on the problem's requirements is made. Options that involve building a custom container from scratch or using less optimized serving infrastructure would likely require more effort and potentially result in higher latency compared to leveraging Vertex AI's pre-built containers and managed endpoints. Solutions that are not specifically designed for low latency HTTP microservices or that require more manual management for scaling, even for a small number of requests, would be less aligned with the goal of minimizing effort and latency. So, in summary, option D provides a solution that directly addresses all the key requirements of the problem. Deploying an XGBoost model as an HTTP microservice with minimal effort and low latency, even for a small number of incoming requests. by utilizing Vertex AI's optimized pre-built containers and managed endpoints. So, it's time to move to the deployment process. Let's quickly start with the model deployment, which is the exciting time when the model is implemented and ready to serve. There are three options to deploy a machine learning model. The first option is to deploy to an endpoint. This option is best when immediate result with low latency is needed, such as making instance recommendations based on a user's browsing habits whenever they are online. A model must be deployed to an endpoint before it can be used to serve real-time predictions. The second option is to deploy using batch prediction. This option is best when no immediate response is required and accumulated data can be processed with a single request. For example, sending out new ads every other week based on the user's recent purchasing behavior and what's currently popular on the market. And the final option is to deploy using offline prediction. This option is best when the model should be deployed in a specific environment of the cloud. An example for this would be sensitive data that has requirements to not be sent externally. In the lab, you practice predicting with an endpoint. Let's explore the endpoints page within Vertex AI. Endpoints are a core concept in a model deployment. There are machine learning models that have been made available to receive online prediction requests from many users. Endpoints are useful for real-time predictions in response to an application request. You can also request batch prediction from an endpoint if you don't need immediate results. As you can see from the image, from this screenshot, the page provides a clear overview of each endpoint, including its status, the model it is serving, the region it is in, and when it was last updated. Okay, now that we've talked about what pipelines are, let's look at this last in this session question. So imagine you have deployed a SkyKey team model to a Vertex AI endpoint using a custom model server. You enabled auto-scaling. However, the deployed model fails to scale beyond one replica, which led to dropped requests. You notice that CPU utilization remains low even during periods of high load. So, what should you do? And the correct answer will be B. Increase the number of workers in your model server. Is correct because this scenario describes a model that fails to scale beyond one replica, even though it has auto-scaling enabled and the CPU utilization remains low. This indicates a bottleneck within the model server itself, not the underlying infrastructure. By increasing the number of workers in the model server, you can allow a single replica to handle more requests in parallel, which addresses the low CPU utilization and dropped requests without needing to scale out to more replicas. The other options are incorrect because they address the wrong part of the problem. So, for example, attaching a GPU is only necessary if the model is computationally expensive and require a GPU to run efficiently. In this case, the CPU utilization is low, so a GPU would not solve the problem. C, scheduling the scaling of the nodes to match expected demand is a good practice, but it does not address the underlying issue of the model failing to scale beyond one replica. And as the last point, D, increasing the mean replica count would not solve the problem, as the model is already failing to scale beyond one replica. So, correct answer is just B. Let's take a look at another simple question. You recently deployed a scikit-learn model to a Vertex AI endpoint. You are now testing the model on live production traffic. While monitoring the endpoint, you discovered twice as many requests per hour than expected throughout the day. You want the endpoint to efficiently scale when the demand increases in the future to prevent users from experiencing high latency. What should you do? So the options here are A. You need to deploy two models to the same endpoint and distribute requests among them evenly. No, I'm in mistake. Because deploy two models at the same endpoint, it will be a totally mistake. Sorry. So the correct answer should be B. Configure an appropriate mean replica count value based on expected baseline traffic. By increasing the minimal number of replica, we ensure the endpoint always has enough resources available to handle the increased baseline traffic, which helps prevent latency issues. So this we need to do to solve our issue. And of course not A. Sorry, I was a mistake at first time. Okay, and next question. You recently used BigQuery ML to train an AutoML regression model. You shared result with your team and received positive feedback. You need to deploy your model for online prediction as quickly as possible. What should you do? So, the correct answer should be C. Alter the model by using BigQuery ML and specify Vertex AI as the model registry. Deploy the model from Vertex AI model registry to Vertex AI endpoint. This option is current because the problem states that the goal is to deploy the model as quickly as possible. The alter model command in BigQuery ML is a specific feature that allows an existing model to be registered in the Vertex AI model registry with a single command. This is the most efficient way to prepare an existing model for deployment to Vertex AI endpoint. The other options are incorrect because they either involve unnecessary retraining or more complex and time-consuming steps. So, for example, A and B, these options both involve retraining the model, which is not quickest way to deploy an existing model. The problem states that the model has already been trained and has received positive feedback. D, this option involves exporting the model to cloud storage and then importing it into Vertex AI model registry. This is a more complex and time-consuming process than using the alter model command directly. Okay, when deploying a model, it's crucial to choose the right deployment hardware. The right choice depends on your specific needs, such as the required latency, throughput, and cost. This is an important part of MLOps that ensures your model is not only accurate but also performs well in production environment. So, quickly, if we explore best practices for model deployment and serving, one of the most important decisions you have to make is choosing the right machine type or hardware for your model. The right choice depends on the type of model you have. As you can see, you can choose between CPU and GPU. A CPU or central processing unit is optimized for widely used general tasks. A GPU or graphics processing unit is an accelerator that optimized for many parallel and distributed tasks. The notes on the bottom of the slide provides more information on the different machine types and scale tiers that are available on Google Cloud. So, to deploy your model for prediction, choose hardware that is appropriate for your model, like different central processing unit, a CPU, virtual machine VM, type of graphic processing unit, GPU types. For more information, I'll share with you specifying machine types or scale tiers. I'll share this information Discord channel and description under this video. So, and here we skipped just question because it's time. I'll share these questions at Discord channel and we quickly discuss it. So, today I'll send to you 4 required courses and asking you to finish production machine learning systems, machine learning in enterprise, machine learning operations, and ML pipelines on Google Cloud. This course is full of interesting videos, few code labs. Believe me, you will get a lot of fun and pleasure finishing these 4 courses. And of course, feel free to share finish it. After finishing, you will get a small certificate. You can share the certificate at Discord channel and of course at LinkedIn. So, okay, this brings us to the end of today's session. Biggest thanks to all of you that you still stay till the end. Today we go throughout 2 big parts. We study a lot. This session was recorded